Hi dear students, today we will discuss about SSB generation methods. You know what is SSB? SSB is single sideband AM, right? In the previous videos we have discussed about SSB and now we will go to the details of SSB generation methods. Basically three methods used for SSB generation. They are filter method, phase shift method, third method. That means there are three methods to generate SSB. Let us see the first method. What is filter method? Filter method is the most commonly used method to generate the SSB signals. Basically, first we will generate a double sideband suppressed carrier signal, and then from that DSB-SC signal we will generate SSB signals. That means first we will generate DSB-SC signal, that is double sideband suppressed carrier signal. That means it contains lower sideband and upper sideband. There will not be any carrier in that signal. Then we will convert that signal into single sideband signals. That means the resulting signal will contain only one sideband. That may be either SSB or USB. And let us see the figure or block diagram for generation of the SSB signals. You can see that first of all, there is a USB crystal or LSB crystal, and that is connected to this block diagram via a switch. That means either USB crystal is connected to this portion or LSB crystal is connected to this portion. Then this section is low frequency crystal oscillator, and that crystal oscillator will produce frequencies that will produce higher frequencies which is used as carrier signal, and that frequencies will be given to the balanced modulator. Balanced modulator is a productive modulator, and the other input to the balanced modulator is audio input. Audio input means lower frequency signal, and it is used as a modulating signal. So the balanced modulator will receive high frequency carrier signal and a low frequency modulated signal, and this balanced modulator find the product of these signals and it will produce a double sideband suppressed carrier signal. That means at the output of this balanced modulator there is a double sideband suppressed carrier signal. Then this signal we have to convert it into SSB signals. So we are applying this signal to the sideband pass filter. That means in this signal there will be two sidebands, upper sideband and lower sideband. But we know that in the case of SSB there will be only one sideband. So we have to pass only one sideband and we have to suppress other sideband. So we are using sideband pass filter. That means it will allow only one sideband to pass to the output. So at the output we will get SSB-SC signal. And this SSB-SC signal will have smaller frequencies, but for the transmission purpose we have to transmit the signal for long distances. So we have to raise its frequency to transmission frequency. For that we have to increase the frequency of this received signal or SSB signal. That is done by the balanced mixer circuit, and balanced mixer circuit is driven by a crystal oscillator, so that this balanced mixer will increase the frequency of the SSB signal like that of the transmitter frequency. And for long distance transmission we have to increase the power of the signal. For that we are using amplify the signal using power amplifier. That means the signal magnitude will be increased by using this linear power amplifier. And this power amplifier, that is for transmission purpose. We are producing this SSB signal for long distance transmission, and for long distance transmission we need to increase the amplitude or magnitude of the signal. That is why we are using linear power amplifier, and then we will be given to this matching network, and then it will be transmitted through the antenna, and this is used for matching network is used for impedance matching, and then that signal will be transmitted through this antenna. That is the block diagram explanation. Let us see the details. That means in the figure balanced modulator produced DSB output, and this contains both sidebands. DSB signal is given to the sideband suppression filter to remove the unwanted sideband. Filter must have flat passband. That means the filter used at the output of this SSB signal will contain flat passband and extremely high attenuation outside the passband. Then the filter suppresses the one of the sideband. The frequency of the SSB signal generated will be very low and compared to the transmitter frequency. That is why we are using mixer circuit. So the frequency is boosted up to the transmitter frequency by the balanced mixer and the crystal oscillator. That means here the frequency is increased. That is what is called a up conversion of the frequency. Then the resulting SSB is amplified by the linear power amplifier and it will be transited through the antenna. So this is a block diagram of the SSB transmitter using the filter method. And next we can go to the second method, that is phase shift method. And first of all, let us see the phase shift method block diagram. We know that this method is used for SSB generation purpose. So first we will see, first of all there will be a modulating signal and we need a carrier signal for modulation. So we are using a carrier source here. You can see here that here you can see different modulators such as modulator, balanced modulator M1 and balanced modulator M2. You can see carrier signal is applied directly to this balanced modulator M2. But this carrier signal is 90-degree phase shifted here by the 90-degree phase shifter, and after that phase shift it is applied to balanced modulator M1. Similarly, balanced modulator M1 receives the modulating signal directly. But you know that balanced modulator M2 receives 90-degree phase shifted version of this modulating signal. See, in the previous method there is no phase shift for the modulated signal or carrier signal, but for avoiding the unwanted sideband we are using filters, but it's a costlier method. So in order to avoid the use of that filters, we are using this phase shift method. So for suppressing the unwanted sideband, we are phase shifting the modulating signal as well as the carrier signal in the phase shift method. Here first balanced modulator M1 receives the modulating signal directly and also it receives a 90-degree phase shifted version of carrier signal. The second balanced modulator M2 receives the 90-degree phase shifted version of the modulated signal and the carrier signal directly. So that is important thing. So at the output it will produce, you know that balanced modulator output will be a double sideband suppressed carrier signal. That means DSB SC signals we will receive. But here you can see, we will do the mathematical analysis, then you will get the concept clear. Here there will be 90-degree phase shifted versions. In both cases DSB SC signal contains 90-degree phase shifted versions, but you know that here one of the sidebands will have the same phase shift, but the other sideband will be out of phase by 180 degree. So when those signals are added at the summing amplifier, that will be cancelled out. So at the output of the summing amplifier, we will get a SSB signal. That means here we will get a DSB SC signal and here also we will get a DSB SC signal. But here the lower sideband, here also there will be a upper sideband and a lower sideband. Here also there will be upper sideband and lower sideband. But here the lower sideband will be 180 degree out of phase, so it will be cancelled out. So the resulting signal will contains only the upper sideband. So this output, that is SSB output, will not be in the will not have higher magnitude. So we have to, for transmission purpose, we have to increase its amplitude. That is why we are using linear power amplifier, so that its magnitude will be increased and then it will be given to the antenna through a matching network. This is for used for impedance matching purpose. That is then the SSB signal, the amplified SSB signal will be transmitted through the antenna. So let us see the details. This consists of two balanced modulators M1 and M2. In the case of M1, it receives the carrier signal shifted by 90 degree and a modulated signal directly applied. And in the case of M2, it will receive carrier signal directly applied and modulated signal will be 90 degree phase shifted. Both modulators generate only sidebands, that is it will contain upper sideband and lower sideband. And seeing the details, M1 produces upper sideband and lower sideband. Each one is shifted by plus 90 degree. and M2 produces upper sideband shifted by plus 90 degree and lower sideband shifted by minus 90 degree. The output of the balanced modulator are added by the summing amplifier. So at the summing amplifier, the two upper sidebands are in phase. You can see that here at the M1 output, both are shifted by plus 90 degree, and here M2 output, upper sideband is shifted by plus 90 degree. So when we are adding these two signals, upper sidebands will be added. But you know that here lower sideband is shifted by minus 90 degree. So two lower sidebands will be subtracted. So it will be cancelled out each other. So two upper sidebands are in phase. So they added to produce a double amplitude signal. The two LSBs are out of phase, that is 180 degree phase difference. So they cancel each other. So output of the summing amplifier contains only upper sideband SSB signal. Similarly, we can see if you are mathematically analyzing the case, we know that there is M1. M1 contains modulated signal, that is sin omega m into t, and it also contains 90 degree phase shifted version of the carrier signal, that is sin omega ct plus 90 degree. Similarly, for the balanced modulator M2, it contains 90 degree phase shifted version of the modulated signal, that is why we are writing sin omega m into t plus 90 degree. It is 90 degree phase shifted. And the carrier signal is directly applied, so we are writing sin omega ct. Now, the output of M1, that is equal to sin omega ct plus 90 degree, that into sin omega m into t, that is balanced modulator M1 multiply these two signals. Similarly, balanced modulator M2 multiply these two signals. You know that it is sin A sin B form. So we know that 2 sin A sin B is equal to cos of A minus B minus cos of A plus B. So we can substitute instead of A and B, so that we will get the output of M1, we will get a sin omega ct plus 90 minus omega m into t minus cos omega ct plus 90 plus omega m into t. So we will get, by rearranging these terms, we will get cos omega ct minus omega m into t plus 90 degree minus cos omega ct plus omega ct plus omega m into t plus 90 degree. You can see that this is a lower frequency because we are taking the difference. So this represents a lower sideband. This is, here the frequencies are added, so it represents a upper sideband. So we, at the output of the M1, we will get a lower sideband and upper sideband. Both are phase shifted by plus 90 degree. Similarly, at the output of M2, we will get cos omega ct minus omega mt plus 90 degree minus cos omega ct plus omega mt plus 90 degree. Here we are writing these terms based on the equation, this one, that is cos of A minus B minus cos of A plus B, where A is, in the case of M2, A is omega mt plus 90, B is omega ct. Okay. For in the case of M1, A is omega mt, B is omega ct plus 90 degree. So when we are writing this equation, we can rearrange the terms as omega ct minus omega mt minus 90 degree minus cos omega ct plus omega mt plus 90 degree. That means this represents, here the frequencies are subtracted, so it represents a lower sideband, and it represents, here the frequencies are added, so it represents the upper sideband. You can see that lower sideband is 90 degree minus 90 degree phase shifted. Upper sideband is plus 90 degree phase shifted. So when we are comparing the output of M1 and M2, you can see that this lower sidebands are 180 degree phase shift, because its phase is plus 90 degree and its phase is minus 90 degree. So total phase difference is 180 degree. So this, when these two signals, M1, output of M1 and output of M2 is added in the, see, output of M1 and output of M2 is added in the summing amplifier, two lower sidebands are 180 degree phase shifted, so they will be cancelled out. So at the output, we will get the double amplitude of the lowest upper sideband. So see, by mathematical analysis, when we are summing this M1 and M2, we will get 2 cos omega ct plus omega mt plus 90 degree. This lower sideband and this lower sideband will be cancelled out because their phase difference is 180 degree. So we will get 2 cos omega ct plus omega mt plus 90 degree. That means here this represents upper sideband because the frequencies are added here. Similarly, we have generated the upper sideband. Similarly, we can generate the lower sideband. So for that, we are giving the carrier signal like this. See, here now the balanced modulator M1 receives the carrier signal directly, and here the balanced modulator M2 receives 90 degree phase shifted version of the carrier signal. So we will get, at the output we will get lower sideband SSB. See, in the previous diagram we have given carrier signal directly to M2 and phase shifted version is given to balanced modulator M1, so that we will get upper sideband at the output. For getting the lower sideband we have to give the carrier signal directly to this M1 and 90 degree phase shifted version will be given to this balanced modulator M2, so that we will get at the output SSB as a lower sideband SSB. So that is the phase shift method. In this we are eliminating the bulky filters to avoid the sideband of the SSB. So phase shift method is much have importance than that of the previous method. Next we are using the third method or modified phase shift method or reverse method, and here we are using 4 balanced modulators, balanced modulator BM1, BM2, BM3 and BM4. Similarly we are using carrier signals, that is audio carrier oscillator is using here. Similarly here also we are using crystal RF carrier oscillator. These two oscillators are different oscillators. Here we are using audio carrier oscillator, that means its frequency is in the range of audio frequency range, that is smaller frequency range, but it will be greater than that of the modulated signal input frequency. Okay, that is this frequency will be, that is its frequency is omega 0 t, that will be greater than that of omega m into t. Similarly here we are using crystal RF carrier oscillator, that means radio frequency will be produced by this crystal RF oscillator and its frequency will be greater than that of the audio carrier oscillator frequency. Here the frequency is omega 1 into t and that will be greater than that of omega 0 into t. And here you can see that this carrier frequency is audio frequency, carrier frequency or subcarrier frequency is given directly to this balanced modulator BM2 and it is 90 degree phase shifted and then given to balanced modulator 1. Here you can see that crystal RF oscillator given its frequency directly to balanced modulator 3, but it is 90 degree phase shifted and given to balanced modulator 4. And also we are using here 2 low pass filters, that is audio low pass filters that will pass only the low frequencies. That means higher frequencies will be cut off. That means it will provide high rejection for higher frequencies, but it will pass low frequencies alone. That means lower sidebands will be passed through this. Similarly here also lower sideband will be passed here. And then at the output side there is a summing network and which is used to add the output from the balanced modulator 3 and balanced modulator 4. So you will get SSB at the output. When we are mathematically analyzing this, you will get the concept. See here. Here audio input has a frequency omega m into t. So this is given directly to both of this balanced modulator. So balanced modulator find the product of these two. Here the balanced modulator receives omega m into t, that is audio input directly and phase shifted version of the carrier signal. So the phase shift is given as omega 0 t plus 90 degree. So both signals will produce a double sideband suppressed carrier signal and its frequency is omega ct plus 90 plus or minus omega m into t at the output. Similarly, the balanced modulator 2 receives audio input directly and it also receives carrier signal directly. So at the output there will be a double sideband suppressed carrier signal. So it will be represented by omega 0 t plus or minus omega m into t. There is no phase shift. That is why we are representing omega 0 t plus omega m into t. But at the upper side there is a phase shift because we are phase shifting this carrier signal by 90 degree. So here we are using audio low pass filter. This audio low pass filter will pass only the low frequencies. That means here there are two frequency components, that is omega 0 t plus 90 degree plus omega m into t, and also there will be omega 0 t plus 90 minus omega m into t. So that means at the output higher frequencies will be rejected and lower frequencies will be passed at the output. Here the lower frequency is minus term, that is omega 0 t plus 90 minus omega m into t. So at the output we will get the lower frequency components alone, that is omega 0 t plus 90 degree minus omega m into t. Similarly here also there is an audio low pass filter and here it will pass the low frequencies alone, it will reject the higher frequencies. What is the low frequencies here? Omega 0 t plus or minus omega m t is the input and here the low frequencies will be omega 0 t minus omega m into t. So at the output of this audio low pass filter we will get omega 0 minus omega m into t. Okay. So now we have the low frequency signals or lower sidebands alone. So that signal will be given to balanced modulator 3. So balanced modulator 3 receives this frequency as well as the crystal oscillator frequencies. Similarly, balanced modulator 4 receives this signal frequency and also it receives the 90 degree phase shifted version of the crystal frequency, that is given as omega 1t plus 90 degree. So the balanced modulator 3 and balanced modulator 4 produces two sidebands, and here the sidebands are given as, you know that first one is omega 1 plus omega 0 t plus 90 degree minus omega m into t plus omega 1 t, that is given here in the first section, and the other sideband will be omega 0 t plus omega, second case it will produces the lower sideband, so it will be omega 1 minus omega 0 plus omega m minus 90 degree. And similarly, in the case of balanced modulator 4, it will produce upper and lower sideband. Upper sideband is omega 1 plus omega 0 minus omega mt plus 90 degree. And at the lower sideband, it will produce omega 1 minus omega 0 plus omega m into t plus 90 degree. So when these signals are added, the phase shifted signals will be subtracted. That means here this is minus 90 degree phase shifted and this is plus 90 degree phase shifted. That means these two signals are 180 degree out of phase, so they will be cancelled out. So at the output we will receive omega 1 plus omega 0 minus omega mt plus 90 degree signals. That's all. Let us see the slide. In this method, only carrier signals are phase shifted by 90 degree. It consists of 4 balanced modulator, 2 carrier signal generators, 2 audio low pass filters and 2 90 degree phase shift network. So balanced modulators are BM1 and BM2. Both have non-shifted modulated signals as input. Oscillator produces carrier signal and BM1 also takes a subcarrier signal which is phase shifted by 90 degree. BM2 takes the subcarrier signal shifted directly from the oscillator. So the output of the BM1 will be, you know that BM1 is equal to cos omega 0 t plus 90 degree into cos omega m into t. This is a carrier and this is the modulated signal. So when applying cos A cos B relation, we will get 1 by 2 into cos omega 0 t plus cos omega mt plus 90 plus cos omega 0 t minus cos omega t mt plus 90 degree. Here in the block diagram, they are representing only the frequency terms. You can see here only frequency terms are represented. Okay. And at the output of the BM2, we will get it is a product of balanced modulator gives the product of modulated signal as well as the frequency carrier signal. So we will get cos omega 0 t into cos omega mt. At the balanced modulator 2, both are directly applied. So we will get EBM2 equal to 1 by 2 cos omega 0 t plus omega mt plus cos omega 0 t minus omega mt. So at the output, we are using 2 low pass filters. The low pass filter with a cutoff frequency f0 removes the sum terms from each of the above signals, leaving only the difference terms as input to BM3 and BM4. You know that low pass filter pass only the low frequency signals. That is why it emits the sum terms and it only passes the difference terms. Difference terms means it will give a smaller frequency, but sum term will give a higher frequency. That is why low pass filter passes only the difference terms. And these signals are identical except the signal applied to BM3 is shifted by plus 90 degree from that applied to BM4. See, in the block diagram you can see that at the output here this is plus 90 degree, but here you can see that there is no phase shift, that is omega 0 minus omega mt, but here omega 0 minus omega mt is phase shifted by plus 90 degree. That is they are saying. So now the crystal RF, there is also a radio frequency crystal at the BM3 and BM4 session, and this crystal RF oscillator produces a high frequency carrier signal which is directly applied to BM3. And also 90 degree phase shifted high frequency carrier signal is applied to BM4. So the output of the BM3 will be EBM3 will be cos omega 1t into cos omega 0 minus omega m into t plus 90 degree. That means this is a carrier, RF carrier signal, this is a modulated signal input. So they will be multiplied to get the product at the balanced modulator BM3. So we will get the output like this. That means here we are applying cos A minus cos A cos B relation here. So output will be 1 by 2 into cos omega 1 plus omega 0 into t minus omega mt plus 90. Similarly, cos omega 1 minus omega 0 into t plus omega mt minus 90 degree. Okay. Next, at the output of the BM4, we will get BM4 will multiply this carrier signal along with this modulating signal, that is cos omega 1 t plus 90 degree into cos omega 0 minus omega m into t. So at the output we will get 1 by 2 into cos omega 1 plus omega 0 into t minus omega m into t plus 90 degree. Similarly, plus omega 1 minus omega 0 t into omega mt plus 90 degree. So at the output we will get two signals. So it will be added by the summing amplifier. That is, output of BM3 and BM4 are added in the summing amplifier to produce the final output. The first two terms are added, but the second terms are cancelled each other. You know that this is the first term in this case. It is plus 90 degree. Similarly, this is the first term in this case. This is also plus 90 degree. That means these two signals are in phase. So they will be added. But you know that the second term, this is plus 90 degree phase. But here it is minus 90 degree phase. That means these two signals will be cancelled out because it is 180 degree out of phase. So at the output we will receive only the lower sideband. So the first two terms will be added and second terms will be cancelled each other. Therefore the final output will be cos omega 1 plus omega 0 minus omega m into t plus 90 degree. That is what is this signal. At the output we will receive the double the amplitude of this signal. Since there is a half here, also there is a half there. So when we are adding, it will goes to 1. There is 1 cos omega 1 plus omega 0 t minus omega mt plus 90 degree will be the result. So this is the lower sideband signal. So at the output we obtained the SSB lower sideband signal. So that's all about this topic. Thank you.